All right, let's get started. Hello, thank you all for coming. My name is Eugene Koifman. I'm an engineer at Hortonworks on the Hive team. So this talk is going to cover transactional operations in Hive. So first I'll describe a few use cases that will explain why we decided to build the system. Then I'm going to describe what the system looks like from the end user point of view. And then I'll talk about the internal design. And then I'll share some performance numbers based on the current work that we're doing. And then I'll talk about the roadmap. So the first use case to consider is, imagine that you have some external data system and you're offloading data from that system into Hive warehouse. So as the data in the external system changes, you have to propagate those changes into the data warehouse. So the traditional way to do that in Hive was to use an insert override statement. And so what it allows you to do is basically read the data in a given partition, modify it, and overwrite the data back. Now, it's OK when you're trying to perform a delete operation, because you can specify in a where clause the rows that you want to filter out. It's more difficult with the updates, since it's more difficult to express different types of updates as a single statement. And also, if you have to update multiple rows, performing this operation repeatedly becomes expensive, since you keep overriding the partition. Now, the other thing to consider is what happens with concurrent operations. So as you're performing this insert override, what happens with readers or potentially other inserts into the system, into the same partition? Well, without anything to manage the concurrency, the behavior is not well defined. Now, Hive has always had this, or at least for a long time, it had the Zookeeper log manager, which supports read and write logs. But the write logs are exclusive, so that means that while this operation is in progress, that means all your read operations are blocked. So if it's a fairly large partition, then that affects the workload. Now, the second use case to consider is continuously ingesting data into a Hive table. So think of some sort of an IoT type of use case where there is something that keeps generating events. Now, one way to do this is to stage the data somewhere in a temporary table, for example, or a file, and add one partition worth of data. Now, the other is basically to do the same thing, except to run an insert statement, which will create a new file in every partition that's affected by the data. Both of these suffer from kind of similar drawbacks, one of which is that it has potential to create lots of small files in the table, which is bad for performance. Alternatively, you can make the batches larger, but then, of course, your users have to wait longer to query the latest data. Now, the third very important use case is the merge statement. Now, if you're coming from a data warehousing background, you're very familiar with it. If not, let me give an example of what that is. Again, it's a way to, it's like a very fancy update statement. It's a way to sort of bring changes from an external system into your Hive table. So imagine that you have a table like this in your data warehouse in Hive. Now, imagine that you also have some sort of a change data capture system where you recorded a window of time from the event stream from that system in this sort of staging table. And what it has is it has a mix of sort of events that should be treated as an update to an existing data in Hive, as well as data that should be treated as an insert. And so with the merge statement, which looks like this, what it allows you to do is in a single statement express in a single command, basically apply all the changes in this staging table to the target table and do that atomically in a single transaction. So what the statement allows you to do, it has this on clause, which allows you to tell the system how to match up the rows between the target and source, which also implies that ideally it has a primary key. And also it has a set of optional clauses, these when matched, when not matched, which lets you instruct the system on what to do, how to update the target table or whether to perform an insert. It also supports a delete clause. So when there is a match, you can also instruct the system to delete the row from a target table. And so the result of that is hopefully exactly what you expect. It integrates in, like I said, in a single statement, all the changes. So the goal was to make these use cases easy in Hive and efficient. One of the key requirements for us is, since Hive is used for long-running analytical queries, is to be able to make sure that these long-running read queries are able to make progress while at the same time, an update can happen or an insert can happen. And you don't have to serialize the two operations. important thing to point out is that this is not an OLTP system. It's primarily designed for kind of slowly changing dimension tables in a, let's say, in a data warehouse. There is no good way in Hive to update a single row the way you could, for example, in HBase. So the cost of running an update statement that matches, let's say, a single row out of a billion row partition or 100,000 rows is more or less the same. So, so you can't really use this to run, like I said, it's not an OLTP system. You can't run hundreds of concurrent update operations. So at a high level, how do we support these? Well, we added a new type of table called a transactional table that supports these update, delete, and merge operations. We also introduced the concept of a transaction into Hive. And this is exactly the kind of sort of ACID transaction that you see in every other relational database. The third module is Streaming Ingest API. And what it is, it's an API that's specifically designed for this IoT type of use case that allows you to ingest a continuous stream of events into a Hive table in these micro batches or micro transactions, but do so efficiently. So from the end user point of view, basically the first thing that you see is a simplest DDL statement to create a table capable of these operations. Now, the first thing to note is that this transaction was true property. So that implies that not all tables are capable of these operations, so you explicitly have to opt in to the feature. Now, the other thing to note is that the table has to be bucketed, which is something that's important. By the way, bucketing in Hive, it just means hash partitioning of the table. So the table has to be bucketed. It's important for later read performance so that we can find the updates to, that you've performed in the system. At the moment, the table cannot be sorted according to user-defined criteria. Both of these are temporary restrictions, but they are there right now. Now, this additional functionality, it has additional requirements on the storage layer used for the table. And these requirements, they are encapsulated in this ACID input format and ACID output format. So as long as the storage format that you're using implements these interfaces, any table can plug into the framework. At the moment, ORC file is the storage format that has implemented these. Now, the current system only supports auto-commit mode equals true. That means one statement per transaction. And the semantics of the read operations, or actually the write operations as well, is that every transaction runs at snapshot isolation. That's the only isolation level that we support. So what that means is that every transaction at the start, it locks in the state of the entire database, or I should say the state of all the transactional systems in the warehouse. And it's not affected by any, by any concurrent update that may happen while the transaction is running. When I say it locks in the state logically. It doesn't actually acquire the lock, so it doesn't prevent updates or delete events or delete operations from happening. Now, in terms of ANSI defined isolation levels, snapshot is somewhere between serializable and repeatable read. So now let me talk about the implementation details. So first of all, I keep talking about transactions. So there is, of course, a transaction manager, which allocates transaction IDs and also keeps track of the state of every transaction in the system, whether it's aborted, running, committed. The storage layer is enhanced to support multi-version concurrency control. And what that means is that every row in one of these transactional tables is decorated with a row ID, which is kind of internal primary key. What it also means is that the system is able to keep track of multiple versions of each row in every transactional table. And this is the key property that allows us to make the reader, to enable the reader to make progress while somebody else is making an update or delete operation. And finally, the table structure or the file structure that represents the table is now richer. I mean, the conventional tables in Hive, you can just basically place a file into the file system and it becomes part of the table. Now, with these tables, it's more complicated, the result of which write is written into something called a delta file, and I'll explain what that is in a minute. So let me run through a concrete example. So here is our trivial sample table, 2 columns. It has one bucket, which is not something you'd ever want to do in production, but just makes the example simpler. So the first thing to note is that the schema of the table changes, right? As I mentioned, every row is decorated with this row ID, and what this row ID, it serves as an internal primary key and consists of several parts, one of which is the transaction ID that has actually initially created the row. The other is the bucket ID and the row ID, which is essentially the sequential numbering of the rows as they're being written to the file. Now, so let's say we start with a simple insert statement that's supposed to add 3 rows to the table. So what happens is first a new Delta file is created, and it has, well, the data exactly what you expect, except that there is this additional column that has this primary key. Now, if you then run an update statement that matches, in this case, the third row of the table, what happens is another Delta file is created, and the new version of the data is written into that Delta file, but with the same primary key, which is how we know that it's actually the same row. Now, let's consider a delete statement. In this case, matches the second row. So again, a new Delta file is created, and the data is written to that file, except that in case it's a delete event, right, you don't actually need the data. It represents, well, a delete event. Now, one thing to point out is that these numbers in the file name of the Delta file, these are the transaction IDs. And this is used later for the system to figure out how to actually read all of these files and make sense of them. The other thing to point out is that in this example, right, I mean, every statement matches a single row. Of course, if you know, if a statement matches many rows, all of them go into the same Delta file. So what happens on read? So on read, the system performs kind of a merge process that is somewhat similar to the way a join works. And basically, for any given row, it has to find the latest version of that row among all the Delta files that it has to consider. So in this case, you know, we're doing a select, and it basically, you know, each file is sorted according to this primary key, and so it performs a process by, you know, looking at each row one by one, looking for update or delete events in other Delta files. Sorry, I think I went too fast here. So the first row here, right, there is nothing in any other Delta file, so that's the version of the data that's returned to the client. Now, for the second row, we see that there is a delete event in the third Delta file, and since a delete event, it causes the system to simply skip that row from the output. And, you know, similarly, in the third case, there is an update event in the second Delta file, so that's the version of the data that's returned to the client. So this kind of merge process happens every time you read the table, every time there are Delta files in the system. Now, as you can imagine, as you perform more and more update operations on the table, you get more and more of these Delta files, so this read process becomes more and more expensive. In order to compensate for that, there is a part of the system called Compactor. And what it is it's a process that runs in the background and proactively sort of proactively rewrites the table and creates something called a base file. And again, note that there are transaction IDs in the file names, and what that means is that the next reader after this compaction process has happened, it knows that it only has to read the base file and can ignore any Delta files with transaction IDs less than that. So at this point, basically, this table is again a flat org file, so reading it is as expensive or as cheap, I suppose, as reading a flat file until you perform more updates. So this compaction process, there are basically 2 flavors of it. There is a minor compaction, which just merges Delta files together, which is fairly lightweight. And there is a more heavyweight process called a major compaction, which actually creates the base file, and it absorbs all the Delta files in it. Now, so in addition to making simply the read process specifically for these transactional tables easier, because right, there is fewer files to merge, it also has potential to make org files themselves more efficient, because as it rewrites the files, it also can fix, if you have smaller stripes, which results in poor compression in an org file. So as this process runs, it rewrites the file, makes org itself more efficient. Now, compaction can be either triggered manually, as you saw in the previous slide, via alter table command, or there is a process that proactively sits in the background scanning metadata, looking for tables that had update or delete operations performed on them. And there are various sort of control parameters that allow you to tell this process when to trigger a compaction process and what kind of compaction process to trigger. So like, for example, you can say every time you notice that there is, you have more than 10 Delta files in a given partition, run a minor compaction, for example. Now, compaction itself is a MapReduce job, so it runs on the cluster. It's completely asynchronous from any other operations on the table. It doesn't acquire any locks. It doesn't, doesn't block any other operations. It does, however, take up cluster resources. Now, again, as the compactor runs and creates new files, old files become obsolete, so there is a garbage collector in the system that figures out when it's safe to delete those. It's called the cleanup process. Now, I keep talking about concurrent operations, so there must be something to manage that concurrency. So I already mentioned the transaction manager. There is also a log manager, which acquires read logs for read operations on all tables, but for write operations, it kind of has to perform different things depending on what kind of table it is. So if it's a transactional table that supports this richer MVCC architecture, the concurrency is actually managed via write-side tracking, which I'll explain in a minute. For conventional tables, it uses, well, the textbook approach is to use a read-write log, right? So as soon as you're writing something to a table, there is an exclusive log, and that prevents all read operations. In Hive, that is oftentimes not what the users are used to, not what they expect. So for that, there is a compatibility mode property that allows you to sort of force the log manager to acquire shared logs for write operations for non-transactional tables. Obviously, the semantics aren't as clearly defined in that case, but sometimes it's sometimes it's useful to do that. State of both of these are persisted in the metastore. By the way, that's also where the compactor, the service where it runs, which is the reason why the system requires a standalone metastore to be part of your cluster setup. Now, for transactional tables themselves, the concurrency management mechanism is done via write-side tracking. So what that means is that every transaction remembers some metadata about what kind of modifications it has performed, and at commit time, or right before commit, it compares that information with the same information that was saved by all other transactions that ran concurrently and have already committed. And if there is any overlap, then the current transaction cannot commit. It will be automatically aborted by the system. So that prevents things like lost update problem, for example. So this really, in Hive at least, it only applies to update operations because two inserts in Hive are never in conflict since it doesn't enforce unique constraints, at least so far. You are allowed to mix sort of the transactional tables and non-transactional tables in the same statement. You cannot write a transactional and a non-transactional table from a single statement, which in Hive is actually, you are able to do that via a single statement called the multi-insert statement. And the reason for that is that if for some reason the transaction fails, these transactional tables, they're smart enough to handle a rollback. The non-transactional tables are not, and so you can't atomically undo stuff. Now, onto the streaming ingest. So as I mentioned, this is an API that's specifically designed for the IoT type of use case where it allows you to continuously ingest events into a Hive table. And the reason that it's able to do this efficiently is it's able to write multiple transactions into a single file and avoiding this problem of too many small files. So basically, the way it works is you call write, commit. As soon as you do that, a read operation can see that data, and it looks sort of with the same transactional semantics. You can also, of course, call abort on any of these transactions, even after the data is written to the file. But since each row is tagged with the transaction ID that creates the row, the metadata in the system remembers that it's an aborted transaction, so the reader will then know to simply skip that data. And so for practical, even though it's written to the file, no reader will actually see that data. So that's how aborted transactions are implemented. Now, this API it's a public API, so it can be used directly, but tools like NiFi Storm, they have all implemented higher level abstractions that leverage this API, so it's probably more user-friendly to use one of those. Whoops, where am I? So this is the same example of the merge statement. How does it actually work? Well, this on clause in the syntax of the statement may have given you a hint. So the way it actually works is the system runs this right outer join between the target table and the source being the preserved side. And the result of the join is basically split into however many when not matched clauses you have. And each of those is written to a Delta file. So in this case, right, the set of updates are written to one Delta file, the set of inserts is written to another Delta file. This is, by the way, of course, the reason why the target table of this merge statement has to be one of these new transactional tables. So once you've created these Delta files, then the read process is exactly the same as we've seen earlier. And, of course, without the merge statement, you can still do this, but it becomes prohibitively expensive if you have more than, a few sort of statements. If you need more than a few statements to express the same logic. So that's basically how the system looks today. Let me talk a little bit about the work that we're currently doing and share some performance numbers based on that. So internally, we refer to it as a split update feature. And so as you remember previously, I showed when you run an update operation, you create a new Delta file, and a delete with a new version of the data is written to that file. So the new layout of the data on disk is it represents the same information as two events. One is a delete of the old data, and the other one is a new insert event. And so logically, it looks like as if the same way as if the client first ran a delete statement and then an insert statement in the same transaction. But it does allow us to internally achieve sort of many advantages. So one of the advantages is that, orc is a columnar format, and it's a kind of a smart storage format, so it supports predicate pushdown. So this enables us to make this predicate pushdown work on all files that represent the part of this transactional table. It's very important for performance, right? The other thing is it improves how we do split computation. So split computation, whenever Hive or Hadoop in general, whenever it reads a file, it breaks it up into pieces, and each task is processing a single piece. So in this system, in order to properly run this stitching process, you have to localize all of these Delta files to a particular task, right, so that it can actually perform the merge. Now, in this new layout, the only thing that needs to be localized is the set of these delete events, which are, by definition, it's a trivial amount of data, right? It's 3 integers, basically. And the Delta file that contains them is itself an org file, so it uses the same compression, and especially considering that a lot of the numbers there, a lot of the integers are actually repeat values, so it compresses really well. So the point is the amount of data that needs to be shipped somewhere is trivial, so that improves network utilization. Also, as part of this feature, it enabled a fully vectorized read path. So what that means that you can pick up batches of data all the way from disk and send them to the operator pipeline. You don't have to sort of convert them into rows. So again, that's a big performance improvement. And one final thing, which actually isn't there right now, but what this new sort of data layout enables is actually allows you to update columns that you're partitioning or bucketing on, which isn't possible in the current system. Now, it's a lot of kind of internal mumbo jumbo. So as the end user, why do you really care about this? And so here is why. So here's the result of one performance experiment, right? It's a 10-node cluster. So what it compares is two things. One is a sort of conventional org table with a flat file as basically a result of a single insert statement versus a transactional table with the same data but populated over 11 insert statements. So it has 11 Delta files in it. So the most interesting part here is the orange bar, I guess, and the green one. So the point here is that the overhead of using this transactional table is pretty much negligible, right? It's single-digit percentages. So you're able to create these new tables that support new new features, new richer set of features without sacrificing performance. So that's really kind of important improvement, great progress. So now about the roadmap. one of the tasks is to support multi-statement transactions. As I mentioned, currently the system is auto-commit. Of course, it would be nice that you can perform whatever number of operations and make them visible atomically. Performance is always on the list, and one of the big ticket items is making compaction smarter. I said that it runs asynchronously from any other activity on any given table partition, but it does take up cluster resources. So the more efficient it is, well, it uses less resources, but also you can run it more frequently, and so that means that this merge process on read time becomes cheaper. Now, another thing to point out is that the current sort of concurrency management mechanism that's done via this write set tracking, it's by definition optimistic. Right now, it's very coarse-grained, so it can create, if you have a lot of concurrent operations, it will detect, it will create false positives and abort your transactions. So improving that, there are easy ways that we can improve that. The other sort of related feature is to add read committed isolation level, but that's where the locking is actually responsible for scheduling transactions to make sure that these anomalies like lost update is prevented. So that way you can make a choice. I mean, if you have low concurrency, you can run this snapshot isolation, which has more, more throughput, or you can run the more conservative pessimistic locking. Improving monitoring, so one of the things so this background compaction process is actually critical for the system. If for whatever reason it's not running, the way you notice it is basically the users start complaining about their queries being slow. And the reason that happens is because the Delta files are accumulating, and you end up, this merge process becomes more and more expensive. So better visibility into what happens with the sort of supporting systems is also a feature to work on. Load data statement. Conventional Hive tables, you can basically just drop a file into it, and then it becomes part of the table. With these tables that require kind of richer sort of structure to these files, you can't do that. So one way to make this work is to support a load data statement, which essentially does almost the same thing as dropping a file in, but in a more controlled way. So it's still kind of a transactional operation, but at the same time, it's near instant way to add, a pre-built file. And the final two things are, so right now, as you've noticed, these tables, they have some requirements like bucketing. You can't have them sorted. So we want to address both of these so you don't have a trade-off, right? If you want to create a table capable of these transactional operations, you don't have to sacrifice anything, whether it's performance or features like SMB join. And this, all of this is kind of, it's not a 5-year plan. It's hopefully 6 months time, all of this will be ready. So a couple of other things. These are the links to the documentation, and the first two and the third link, that's a link to the Jira system. So if you want to follow the project in more detail or contribute some patches, you're very welcome to do that. And if you have any issues, there is a user and dev list, so you can send email there, somebody will respond. So that's all I have. Thank you. I'll take questions. No, you have to write them through Hive. Yeah. Oh, so by the way, the question was, can you create these org files, asset compliant files through Spark? And the answer is right now, no. So, okay, so the question is, how do you convert an existing table into one of these transactional tables? Yeah, so partitioning here works exactly the same way. So the second question is, how does partitioning work? Partitioning here works exactly the same as with all other tables. Now, with respect to converting a non-transactional table to a transactional table, if you started out with a table that satisfies the properties that it's an org table and it's bucketed, then there is actually, it's basically a metadata operation. You can run an alter table command specify this transaction equals true property, and then the compactor, when it gets to it, it will rewrite the table and assign these primary keys to the rows. So that happens in the background. If you start with, text or whatever, then you have to do insert, as select. Yes.
Well, is your kind of table and the block size that you have to respect one to wait size of megabytes of file size.
Okay.
So it's still the same. Should I? What is?
So this system doesn't sort of dictate anything specific in that sense, right?
It's still the same.
Yeah, it's basically the same as any other org-based table.
You have a lot of transactions with few.
Well, right. So if you're creating transactions that have 10 rows each, that will be a problem. But the compactor will, in the long run, will fix that, right? So every time you call commit, you close a stripe in the org file, right? So basically the consequence is that you have small stripes. The compression is not as good, right? So the compactor, as it runs, it will rewrite the table, right?
So currently the compactor, you said it's running on demand or it's automatic, right?
Mm-hmm.
So is there like finer control, like is it at the user level or at more at the metadata level or like admin level?
So there are two ways to trigger compaction, right? You can run an alter table command and actually specify partition on which you want the compactor to run, and so it'll run on demand. The other way is this automated way where there is a background process that constantly scans the metadata, and then it will launch it. Am I answering the question?
Yeah, so what is the frequency? Do we have control on that frequency?
There are various controls, though it's not time-based, it's based on, for example, right, the reason that we run compaction is because, right, as you have more delta files, right, the read becomes more expensive. So you control it by saying, once you see, let's say, 10 or however many delta files, then run a minor compaction, for example. Once you see that the ratio of, let's say, the data volume in the base file versus the sum total of your delta files, run a major compaction. So there are, yeah.
Do you have any limitation for the compaction, especially for the Hive, the transactional Hive table? If like the 1 billion rows, and your compactor to rewrite those kind of table, or like
No, it will, however many rows you have in your table, that's what it will rewrite. So basically, right, you can think of the base file and then some delta files, right? And then it will merge them, doesn't matter how much data is in there, right? So it itself is a MapReduce job, right? So it's parallelizable.
maybe performance delays or issues?
So right now, since we require bucketing, the parallelism of this compaction job is however many buckets you have, right? So if you created a table with 4 buckets and it's an enormous table, that limits the parallelism, right? But so, how should I put it? The thing that you want to avoid is where you're creating new delta files faster than the compactor can actually absorb them, right? So in that sense, yes, there is a performance. Otherwise, it's a completely background process, right? So its performance isn't that important, right? Does that make sense? Okay.
Can the transactional tables take advantage of LL18?
So on the read path, yes, and there is currently work going on to enable caching for these tables. So yes, and soon it will be better, I guess. So the short answer is yes.
So I guess an update comes in and perhaps the data is cached. Would it fly down in the delta files to update the cache, or could you potentially get a stale result?
Well, so how should I put it? No, you can't get a stale result. And the updates, they're not happening in place, right? So when you create an update, you're actually writing a new delta file, right? So with respect to the cache, whatever was in the cache is still there, except that the delta files there will have old transaction IDs. So it'll essentially cause more data to be loaded into cache. Right? Compaction? So you can fire it manually, but there is also a system process that will be triggered automatically.
Do you see any problem with the tables accessing through Spark?
So right now, you cannot read these tables through Spark.
Cannot read?
No. So the system has no integration with Spark.
I think this kind of transactions table, when we have this kind of integration with Druid, it's supposed to be so fast as Druid, for instance. I mean, when you have LLFA on this table, this kind of mix is supposed to be fast as Druid as, for instance, because for me there is a kind of overlap between these two tools.
I don't have any numbers with respect to Druid, so sorry, I don't have an answer.
Okay.
Yes?
Elaborate a little about the compaction. What happens if file was a little bit while background?
I'm sorry, can you speak up?
What happens if I want to read the text while the background compaction is in progress?
That's okay. They can run completely in parallel. No conflict, no. It's because the compactor basically creates a new file, right? So when the read operation starts, it asks the transaction manager, give me a state of all the transactions in the system, like whether they're committed, aborted, etc. And since the files, they have transaction IDs in the names, right? The system will only read the data with respect to that list that it got. So the compactor, it creates a new file, which essentially, how should I put it? It wasn't even available at the time the reader started. So it's completely, excuse me. So it's completely parallel. That's it. All right. Thank you all for your time.